All right, guys. So now we're going to talk about chapter 15, which is an introduction to waves. So we're going to talk about wave motion in chapter 15, give you introduction to the basic ideas of waves. And then chapter 16 is sort of like an application where we look at specifically as sound waves. So this series of images perfectly demonstrate what in a way wave is. So if you look at the first image, there is, you have a still, lake. So the water is undisturbed. And then let's say you throw a rock into the water. So the second image, what it does, it basically created a disturbance in water, which acted like a source of generation of waves. And then you can see, right, waves in images 3 and 4 then start propagating, right, spreading out into the, that region. That means wave itself is basically a disturbance in some kind of medium. So we're going to see that there are mechanical waves and electromagnetic waves, and the chapter 15 and 16 mostly concentrates on mechanical waves. That means this is a water wave. There would not be a water wave if there was no water. That means there's a requirement for a medium. That's what the mechanical waves requires. So a mechanical wave is a disturbance in specific medium, and then it generates waves that can then propagate outward. All right. So the units for this chapter are, we talk about wave motion, characteristics of the wave motion, types of waves. These are already, we're considering mechanical waves, right? So the types of mechanical waves, transverse and longitudinal. And one of the things we're going to see here, waves um, are specifically carrying information and energy. When you create a water wave, the wave doesn't move the medium itself. So when the wave is moving, right, the water itself is not moving. Water technically, goes a little bit up and down, a little bit back and forth, but that's about it. What what the wave does, it transports energy. Well, with energy, then we can sort of like get information. All right, so then we're going to talk about mathematical representation of traveling waves. So we're going to look at the wave equation, and then we're going to look at some applications. So the principle of superposition, reflection, and transmission. There's also interference, which is very unique to waves. Only waves can interfere, which in a way means that they can overlap without destroying each other. Then we're going to look at another application, which is a standing wave and resonance. And then, briefly cover refraction and diffraction. The last two things going to be extensively covered in later chapters when we get into optics. But, here I'm going to give you a little bit of, taste of that, refraction and diffraction. All right, so let's start with, probably the simplest wave we can have, which is a string wave. So you can see, right? So you're holding a string, and then you create a disturbance by, just pushing it upward. You push it upward, and what you're doing here, you basically create this tension in the string, which then generates this pulse. So then you push up or down, right, one time, up or down, and then you create a pulse. Okay, so the single wave is known as a pulse. And you can see then this pulse starts moving to the right, right? So let's say it changes its position to the right as a function of time. So then if you look at this delta x, right, the displacement, and over delta t, right, also the time it took for this, this particular pulse to go from point A to point B, then we can see that there's also distinct velocity. So there's also like a velocity of the wave. All right, so what we're going to do here, we're going to look at continuous waves that start with vibrations. And in chapter 14, we talked about simple harmonic motion, which exhibited sinusoidal motion. And in a way, we're going to see that same idea can be then also used in this chapter. That means waves also, behave sinusoidally. And if you're looking at the wave, you can describe everything in terms of sine and cosine functions. All right. So here's, so like a string wave. Imagine like, let's say you're generating pulse after pulse after pulse, and then you basically see something like this shape. So a couple of important things that we can have about a wave would be the amplitude, which is how high or how low it goes with respect to sort of like as a central line. That means you draw a line exactly to the center, to the middle of the shape, and then amplitude is sort of like, let's say if you take this to be the x, this horizontal line as an x-axis, and let's say this is the y-axis, then in a way amplitude is how high or how low it goes with respect to the y-axis. So we can say that this is, let's say, plus a, and this is then minus a, very similar to the simple harmonic motion graph, right? So this is actually the graph of a vertical position of a wave with respect to its horizontal position, not with respect to time. So this particular graph is, because it represents actual wave, you're looking at in terms of the string itself, right? How it behaves, and part of the string, how high it goes, how low it goes, as a function of, position as the wave itself is propagating to the right with some velocity. Then once we measure, let's say, the amplitude, which is one of the important things that we usually need for the waves, we can also measure the, let's say, the distance between those high or low points. So let's say, for example, the positive amplitude of a wave is known as a crest. The negative amplitude is known as a trough. So then a distance from one crest to another crest is known as a wavelength. And the reason it's known as a wavelength, because if you are trying to draw one wave, then it will be a shape that starts, let's say, from one point, let's say from a crest, and then it goes and comes back to the same point again. And that's basically one wave. Because after that, it just repeats the shape, right? For example, again, if I, let's say, take this point, then that means, basically I'm looking at the position of the wave on exactly horizontal axis, with an increasing, right, the shape. That means increases, then goes to horizontal. See, it comes back to horizontal, but here it's decreases. So that means it's not the same shape anymore. So it goes, comes back, and then here we can see again horizontal and increases. That means that's basically where we stop. So then this is also one wavelength distance. That means one wavelength is going from one point of the wave to another, when after that it again repeats exactly the same thing. Okay. Wavelength has units of meters. Amplitude has units of meters. Those are measurements of length. And other things that, let's say, we can measure is if I'm looking at this exact same, let's say, motion of a wave, but as a function of not position, but let's say as a function of the time in seconds, for example. Then, I'm looking basically how this shape is moving as a function of time. Then the distance, let's say it's not a distance anymore, right? Basically, it's in terms of, let's say, the time interval. So, for example, I choose a point here and I say, okay, so this is going to be my point of interest. Then I have this crest over here, right? And since this wave is moving to the right, I want to see that, let's say, how long will it take, let's say, for this crest to go from here to there? That means how long does it take for this crest to travel from here to there? And that is known as one period of time. That means the time it takes for, let's say, this crest starting from here to go to this position, the time it takes for basically for that one crest to go from one point to another is known as a period. Okay. So period is then the time for one cycle, one oscillation. We have used period many times already. So that's basically what it means. So it generally comes in units of seconds. Frequency is then 1 over the period, which represents how many, let's say, crests go through that, let's say, cycle, right, as a function of time. That means how many, let's say, crests go in 1 second through that point. You can have tens, crests go through that point in 1 second, or we can 100 or 1000. Then you can say that, you know then you have 1000 hertz as a frequency. That means the frequency, basically the number of cycles per unit time, period, the time for one cycle, basically the time for, time per cycle. So like, let's say that's why they are reciprocals. So then the velocity of a wave can be, calculated by simply, let's say measuring how, let's say how long. Yeah, so kind of like, let's make it a little bit clear. So think like this. So points of interest are this point and that point. So that means if this crest here, point A, right? If this crest here goes from point A to point B, because the whole thing is shifting, right? It goes from point A to point B. That means I can say that the distance it covers is one wavelength. Distance, let's say, it goes from point A to point B, right? When this particular crest goes from point A to point B, it covers one wave equivalent distance. But also the time it takes for it to cover that distance is then the period. Remember, speed is what? Is distance over time. Distance is one wavelength, time is one period. So then the speed of a wave is given as the, wavelength over the period. But since frequency is 1 over the period, I can also write this as wavelength times frequency. And that's probably most commonly writing the wave speed. Wavelength times frequency, but obviously that's pretty much because it's wavelength distance over time, wavelength over the period. We just write it in terms of wavelength times frequency. So that's, in terms of some of the wave characteristics: amplitude, wavelength, frequency, period, and the wave velocity. Because this is true for any type of wave: traveling wave, standing wave, transverse wave, longitudinal wave, mechanical wave, light wave, electromagnetic wave, right? Doesn't matter. This, let's say 1, 2, 3, 4, 5 quantities are exactly, the same way you can find, right, for any type of, any type of wave. All right, so here I want to kind of demonstrate how we can, let's say, generate a pulse, and we're able to see like how the wave is traveling. So let's say that there's no end over here, and things like this. So you have, I don't know, like, let's say marble string or something like that. So, and let's have maybe a ruler. So you can see that, if I place it here, so we're gonna have a pulse, and well, let's do that manually first. So think like this: the wave, to create a wave here, I need to have a disturbance. So I take it and just move it up or down. So let's say I create a single pulse. So here how I create single pulse. So now you can see, right, it's moving. So I create a single pulse. It is moving as a function of time. And if I do up or down, up or down, up or down, see, I can then create those waves. Those are known as traveling waves because you can see, right, they are traveling as a function of time. So then, for example, then let's do a pulse here and have a you can see, right, it's a single pulse. It creates like that. Here I can, change the amplitude. So now it's higher, width, and everything like that. What I'm going to do, I'm going to have no damping. That means, all the waves then have the same exact crest. If I do, let's say, damping, then, the crest eventually, let's say, dissipates. But what I have here is this. So let's say if I'm oscillating, you can see that what we do, we create a wave like this. And the waves, you can see, right, moving as a function of time to the right. So these waves are moving with some velocity v. But look at, for example, if I pause for 1 second, look at this marble over here. So this green one over here. See, this marble, as the wave is moving, it's not moving, to the right with the wave. All it does, it actually goes up and down with respect to this, its axis. It means it just goes, up and down. As the wave is moving to the right, the medium, right, goes up and down. Same thing you can see, for example, with this one. All it does, it just goes up and down, perpendicular to the direction of the motion. So let's look at it again. See those green marbles, right? They just go up and down, up and down. But the wave itself, you can see, right, the crest, right, definitely. So let's say I'm moving. So that's why one thing I can do here is I can let's say pause, and I can say, all right, so I'm going to look at in terms of how this guy going from here 2 meters, right? Going to go from here to there, for example. See, this is the next crest. That's a 4 centimeter distance. Okay, now that's my wavelength. Wavelength then is 4 centimeters. I mean, it's a measurement of length. So here you can put it like centimeters, it's okay. So let's say it's 4 centimeters. Now I have the wavelength to be 4 centimeters. Then I can also measure, let's say, the time. So if I have, for example, a timer, right? And then I start the timer from here, and in terms of as soon as I start the animation, I want to look at, let's say, how this wave is moving from 2 centimeters to 6 centimeters, right? Let's say this particular crest of interest. Then I can also measure then the period, how long it takes for it to go to the position of a you know another crest. So if I have then the wavelength and the period, I can calculate the speed of the wave, right? So let's say if I do that, well, approximately, oh, I forgot to start the timer. So let's say if I start the timer, okay, so about 0.65 seconds. Then if I go, let's say, zero point 0.04 meters divided by 0.65 seconds, then I can calculate the wave of the speed. So then the wave will be 0.04 divided by 0.65. So that's 0.0, let's say 6 meters per second, which is roughly 6 centimeters per second. Okay, so that's basically in terms of the speed of this wave. Okay, so I could have also calculated that by 0.04 meters and then times frequency that I have over here, again would get exactly same value. But the idea here is this is pretty much what you're getting with the what we call transverse wave. So we're going to talk about that in a lecture, in the slides for 1 second. But kind of like, let's say if the wave is moving, the distance between one crest to another crest, that's the wavelength. How long does one crest take to go to the position of the crest ahead of it, right? Then it's also then the period. We can use all of those things then to calculate, let's say, velocity of the wave. All right, so let's then go back to our slides. So that's kind of what we have. Now we have two types of waves. We're going to see that there's a transverse wave where the medium itself, when you create a wave, medium itself goes up and down, just like you saw with that wave, right? It just goes up and down. And then you have longitudinal wave, which basically goes back and forth with respect to the, let's say, with respect to the direction of the wave propagation. That means here the wave is moving to the right in both cases, right? The wave is moving to the right, but the medium goes up and down. So perpendicular to the wave direction, the medium itself, the motion of particles in the medium. And the longitudinal, when it's parallel to the medium, right, moves back and forth parallel to the direction of the wave. All right. Again, it's probably easier to visualize if there's a animation, and I have one that I can share it with you quickly. All right, there you go. So you can see right at the top you have then transverse waves. Transverse waves basically, see the medium just goes up and down and things like that. Where here you have the longitudinal waves, you can think of like as a sort of like those particles connected by a string. So you can see the difference, right? So here, if you're looking at any type of particle, it just goes up and down, up and down, up and down. And here, if you're looking at some kind of particle, so it goes back and forth in the direction of the motion. So in both cases, the wave is moving in that direction to the right. But the medium either goes perpendicular, so it's a transverse wave, or parallel to the direction of the motion. In that case, it's a longitudinal wave. All right. So those are the two types of mechanical waves, transverse and longitudinal. Technically, some of the electromagnetic wave is also transverse wave. So when we go to, let's say, light in the future, it also can be considered as a transverse wave. Sound is a longitudinal wave, for example. String wave is a transverse wave. The sound is generated by the air molecules. So when there is a sound, like let's say a speaker, right? So the speaker just oscillates back and forth. So you can see, right? So let's say this is the speaker. So what it does, there's sort of like, let's say, a membrane, right? Just oscillates, back and forth like this, the drum membrane, back and forth, and it pushes and pulls the air molecules, pushes and pulls the air molecules, and it creates then the region, where you have a dense packets of air molecules, and then not so dense, and those are pretty much in terms of, like, let's say, density of air. And you can think of like this. This is known as a compression, where it's more dense, and then you have then sort of like expansion, where it's less dense. Then this compression can be modeled as the crest of this wave. So crest and a trough, crest and a trough, crest and a trough, and something like that, right? So they can model it as like that, in terms of wherever you have a compression, that's the crest, expansion, that's a trough. And then you can see, right, the distance from here to there, this is a one wavelength distance. And going from, so let's say, going from here to there, right? So let's say one crest moving another crest, right? They're all kind of moving with some velocity v to the right. We're going to have another entire chapter on sound waves. That's chapter 16. All right, so now one of the things we have about the string waves is that I mentioned earlier, right? That when you take the string and start, pushing it up and down, you technically, create sort of like a tension in the string, and then tension then allows us to generate those shapes. And the tension is then actually part of the equation for the velocity of the string. We can assume that it can then be used to calculate the velocity of the string, because how hard you push, right, can also determine, how fast your wave is moving technically. So for example, if you take this string over here, and then let's say you take then the L to be the length of the string, and then M to be the mass of the string, then one thing we can do, we can calculate what we call linear mass density. Linear mass density given with mu. So this mu over there, right? So the mu is equals to mass of the string divided by length of the string. So it's a quantity that represents how the mass of the string distributed over its length. Because how fast the wave will be moving also depends on those quantities. Heavy strings will move, a little slower. Light strings, I'm talking about wave, right? Wave generated on those strings. So the wave generated on a heavy string will move slower. You can try it yourself, right? Take something that is, a cable or a wire that is heavier, try to create a wave and see how it's a pulse, how it's moving. And then you take something really light string and try to create a wave and see how it's moving. Because one thing we have here is we can see, right, the speed is proportional to the square root of tension, but inversely proportional to the square root of mu. Okay, that means since mu is then mass per length, heavier string give you lower speed. Okay, that means this equation, right, where the speed is equals to square root of tension over then linear mass density, specifically works for the strings. You can't really use this for other waves. Let's say water wave or a sound wave. We can't use that because this is specifically for the tension in the string, mass of the string and length of the string, right? And we can then see that, let's say when you're oscillating, right? So you create a pulse. There is this, a tension force. So the tension force has components, and one component that is basically is effective for us, right, can then be used in the calculation of the speed. Again, this equation specifically works for the string waves. And let's say string like this, right, or a rope or a cable or something like that, right? Then speed, wavelength times frequency is more general, works for every type of waves. This one works, this equation, right, specifically for the string waves. So we can also look at in terms of velocity of a longitudinal wave that depends on the elastic restoring force of the medium on the mass density. So this is then in terms of the speed equals square root of E over rho, or V equals square root of B over rho. Now, E and B are those elastic properties, where the E itself, if you remember from the earlier chapters in physics 37, so E here is then the Young's modulus. So, or elastic modulus, like elastic modulus. Okay. So then we can use that for this equation. And then the rho here is then the density, right? It's density. Okay. Where B here is then the bulk modulus. Again, rho is its density. Now, these equations then can be used for, let's say, specific purposes. For example, these are the you can say these are for longitudinal waves. So this first one over here we can use for traveling wave moving in a liquid in a solid rod. So let's say if it's moving in a solid rod. So let's say solid rod, the wave moving. So this one, let's say solid rod. And second equation here, we can use it for if it's moving in a liquid or gas. Moving in liquid or gas. Okay. Because yeah, right. So you can have a sound propagating through the wires, right, through the transmission lines and things like that, or you can have sound propagating through air, or let's say through water and things like that. So this equation then can be specifically for that. All right, so let's look at an example here. So you have a 25-gram string is under 20 newtons of tension. A pulse travels the length of the string in 50 milliseconds. How long is the string? So again, you can see we're dealing here with a string wave, right? So you're given, so let's say you can write it down in terms of what is given to you. So you're given mass of the string, 25 grams. So let's say 25 times 10 to the negative 3 kilograms. Then you're given tension, which is 20 newtons. And then you're told that it is, the pulse travels in the length of the string in 50 milliseconds. That means, how long it takes for it to go, let's say, from point A to point B. So then pretty much, let's say time is 50 times 10 to the negative 3 seconds. So what we want to find here is how long is the string. So length L of the string. Okay. So one thing we have here is this. We know from, one of the earlier, equation that we learned is that speed equals distance over time. That means the speed at which this wave, will be propagating, this pulse, right, will be propagating equals distance, which is length of the, let's say string over the time. So V equals L over T. That means L is equals to 10 V times T. So that means that distance, right, is the length of the string is speed of the, pulse times time. All right, so we are given the time, but we're not given the speed. But we know because it's a string wave, the speed is square root of tension force divided by mu, then times time. All right, so tension force we're given directly, but mu we are not given, but mu is then the mass of the string divided by the length of the string. That means if I come back here, I can say, okay, length is equals to square root of tension force divided by then mass per length times time, which means then it's square root of tension force times length over mass then times time. Okay, that means I can't calculate this because I have length that I want here, inside the square root over there, right? Okay, that means we have to find a way to kind of, remove that. All right, so what we do is just, let's say, square both sides. Okay, then what I have here is then length square is equals to tension force times length over mass, then times t squared. That means this is what we get. And then here, technically, then I can get rid of that. So then my equation is L equals then tension force over mass times time squared. Now I can plug in and find the length, which is 20 newtons divided by 25 times 10 to the negative 3 kilograms, and then times time squared, which is 50 times 10 to the negative 3 seconds squared. What we get here is then 2-meter length for the string. Again, so this was the key, was to use this equation, right? Speed equals to then tension over, linear mass density. All right. Let's look at another example here. A string 1 has linear density 2 grams per meter, and string 2 has linear density 4 grams per meter. Okay. That means one is lighter, string 1, the other one is heavier, string 2. A student sends pulses in both directions by quickly pulling up on the nut, then releasing it. What should the string length L1 and L2 be if the pulses are to reach the ends of the strings simultaneously? All right. So here, in terms of then, let's again write down what's given to us. It's a good practice to, put everything in front of you so that you can easily see, let's say what you have. Again, always I recommend read the question twice. You read the question once, and then when you're reading it second time, write down what's given to you. All right, so we're given mu1, and mu1 is 2 grams per meters. All right, I'm going to keep it in grams, and I'm going to explain why in a little bit. Mu2 is equal to then 4 gram per meters. Those are my density, linear mass density for 1 and 2. Now, one thing we have here is this. If you remember, I mentioned that the speed of the wave is different depending on how heavy the, let's say, the string is. And you can see, right, this one is 2 grams per meter of the length of the string. This one is 4 grams for each meter of the string. That means string 2 is heavier. That means we already know, right? So even though, let's say, when you pull and let go, there's going to be the same tension in both strings, the speed of the wave is going to be different because of the, one is heavier compared to the other one. All right, so we're also given that the distance here is basically 4 meters. Okay, so I guess we can say that this is L1 plus L2 equals 4 meters. So that's one thing we also have. All right, so then what we want to find is basically L1 and L2. Those are two unknown distances, or, in terms of how are they related, right? How is one compared to the other one? Is it double, triple, half, and things like that? All right. So as I mentioned, speed of the pulse that we generate in string 1 is different from string 2 based on this equation. Speed 1 is equals to square root of, f of t. And f of t, as I mentioned, is the same because we pull and let go with, basically under same condition for both of them. So f of t over mu1. Then v2 is equals to square root of f of t over mu2. Right, so this is basically what we have in terms of that. Now, generally when you have two things like this, and they are sharing some common, quantity that is constant, that means one quantity is same for both of them, and that's tension. That means I can use that to equate them. So for example, see if I take the, let's say take the, square both sides. Then what I have here, v1 square equals f of t over mu1. V2 square equals f of t over mu2. And then I can say then f of t1, sorry, f of t is the same for both of them, which means that, see, if I move this mu1 over here, that means f of t is equals to mu1 times v1 square, but it's also equals to mu2 times v2 square if I move it here. That means, I can write those things in terms of that. That means I can say mu1 v1 square equals mu2 v2 square. All right. Now, we go back, we can see that we're not given any information about speed. I have mu1, mu2, right? But I don't have any information about the speed. But I know one thing. What is speed? Well, it's a distance over time. So that means I can say, all right, so v1 is equals to then distance it covers, which is L1 over the time T1. V2 is equal to distance it covers over the time T2. But we know that they get there simultaneously. That means T1 equals T2, which means I can come back and I can say mu1 times L1 over T then equals mu2 times L2, sorry, this is squared, right? L2 over T squared. And since the time 1 equals time 2, I can technically get rid of the time. And what I end up with is this, mu1 L1 square equals mu2 L2 square. All right. So, and this is what I want. See, I have left side and right side only in terms of one thing that I know and one thing that I don't know. So then from here, what I can do, I can do the ratio. See, if I do the ratio where L1 over L2 square, right? If I cannot do that, then, or even, one thing I can do here is this. I take the square root of both sides, and then which will give me this. If I take the square root of both sides, I'm going to have then square root of mu1 times L1 equals, square root of mu2 times L2. Then I divide both sides by square root of mu1 L2. So, or I can just do this. Let's say L2, right? And then divide both sides by square root of mu1. That means then I can say then L1 is equals to the ratio of the square root of mu1 over mu2, sorry, mu2 over mu1 times L1. So remember, I left everything in grams. That's because here I can just do that. I can just say that this is 4 gram per meters over 2 grams per meters times L2. This is L2, which is, 4 over 2, 2, square root of 2. So I get then square root of 2 times L2. That means L1 is then equals to the square root of 2 times L2. That means, this is equals to square root of 2 times L2. That means it is longer than L2, but exactly by that much. So square root of 2 is just basically 1.5, 1.4. So it's roughly, you can say roughly 1.4 times longer than L2. That's why the pulse in string one moving faster, but it covering longer distance. So that's why it takes a little bit, still the same time, even though, in the string two here is shorter, string one is longer, but it takes them exactly the same time. Only under this condition it can. If they had the same distance, if this knot was exactly at the center, then they would not reach the other ends, right, simultaneously. All right, so that's what we had over here. Well, we can even, go further and technically calculate all these values in terms of giving us specific value. Like, let's say, all right, so because we're given this, a 4 meters, and we know that L1 plus L2 equals 4 meters, then in a way I can say that L1 plus L2 equals 4 meters, where L1 is then square root of 2 times L2 plus L2 is equals to 4 meters, right? So then I can use this, simple enough, right? Factor out L2, then square root of 2 plus 1 equals 4 meters, then solve for L2, which is, let's say, 1.7 meters. Then go back to this equation again and solve for L1, since now I know what L2 is. So then L1 is equals to then 2.3 meters. And we can get exactly values of L1 and L2 in terms of that as well. All right. So let's look at then in terms of um, those two types of waves that we talked about, transverse and longitudinal. So you can see, right, earthquakes produce both longitudinal and transverse waves. That means, you can have strictly just transverse or just longitudinal, or you can have something that is combination. So technically water wave is also a combination of both. So in this case, you can see earthquake. So you have both types can travel through the solid material, but only longitudinal waves can propagate through a fluid. In the transverse direction, a fluid has no restoring force. So surface waves are waves that travel along the boundary line or boundary between, two media. That means you can have, like let's say more complicated waves like, earthquakes or water waves and things like that. But obviously, one of the things we will do here, we try to concentrate on some more simple, not necessarily simple, but a little bit more straightforward, either transverse or longitudinal, right? So that's why some of the applications like standing wave is just transverse, and then sound wave is just longitudinal, right? To study them a little bit, greater detail. All right, so important thing about wave is that it carries energy. And when it carries energy, we can, calculate. All right, so you can see, right, by looking at the energy of a particle of matter in a medium. So let's say you have a wave is moving and goes through that, some kind of material like that, that has a length L, and then it will travel as like, V times T. So we can say that energy equals 1/2 Ka square. Remember, that was the energy that we, used also in a simple harmonic motion, right? 1/2 K times A square. But we can rewrite it in terms of this format. Now, what does it, equation come from? Well, we are basically, what we're doing, we're replacing K with other information. Because one thing we know about, K here is that there's an equation that relates K and frequency. Because remember, omega was equals to 2 pi times linear frequency. But omega was also equals to square root of K over M. That means one thing we can do here is we can relate those. That means K over M, sorry, also equals to 2 pi times F. So then you can see, right, if I then square both sides, then what I have here is I have K over M equals 4 pi square F square. Move the M to the right, then I have that for K. That means K equals 4 pi square F square times M. That means what I did here, I just came and replaced this K with that, and we got then this equation. Okay, the idea here is that we are looking at the equation, right? So that it is represented in terms of the amplitude, then M represents sort of like the mass of that, the particles, right, in that medium, and then linear frequency. Okay, so this is, in terms of how this 1/2 Ka square was just, a rewritten in terms of then mass, frequency, um, let's say, and amplitude. Okay, now then says, then assuming that entire medium has the same density, then what we can do here is we can calculate the intensity. Okay, so intensity is equals to P, which is the power. If you remember again, P is the power, which is energy per unit time. That means the rate at which energy is transformed or transferred. So energy per unit time divided by S. Now, what is this quantity S? Well, that's the area of that medium that we're considering, through which the, let's say, that surface area, right, of that medium. That means what we have here is, if I'm then writing this is the area, and then this is the length of that medium, then in a way volume is equals to, if you remember, right, area times length. So I can write the volume as area times length. Then what I can have here is this. This is basically volume, not the velocity. So this is surface area times length, and then this is surface area where length can be replaced as v times t. Okay, surface area times velocity times time. So then when I come back over here, then I can write this in terms of intensity is equals to power divided by the surface area. Well, intensity power is then energy per time, then per surface area. That means, in a way, intensity described like, let's say, the rate at which energy is passing through that, a medium, as a function of time and as a function of surface area. All right. So then from here, what I can do is I can rewrite energy in terms of 2 pi square m times f times amplitude square. Then this is then divided by t times surface area. Now, but there's some information over there. There's, for example, a velocity and there's a density. Where do those things come from? Well, remember, density equation is mass per volume. Well, which means that I can replace then the mass in energy equation, right? Mass in terms of then density times volume. So then this becomes density times volume. And well, this is my volume, right? It's the surface area times remember, it's surface area times length, or surface area times speed times time. So times speed times time times surface area. That's what the volume is. So I replace that. So when I come back here and I can write this 2 pi square, so replace mass with that. Density, speed, time, then surface area, then times then the frequency square, then times amplitude square. Then this is divided by the time and surface area, which are those two. Then you can see, right? Time cancels out, surface area cancels out, and this is what survives. And this is the equation for the intensity. So intensity um, is proportional, we can see, right, to the square of the frequency. So intensity is proportional to the square of the frequency and to the square of the, amplitude. Okay. That means, larger the higher the frequency of the wave, more energy it carries. Larger the amplitude, more energy it carries. That means generally, that's why, for example, uh, ultraviolet has more energy than visible light because it has a larger frequency. Gamma rays and X-rays they have much higher intensity and energy because they have larger frequency. You can say, right, energy itself is proportional to the frequency square. Larger the frequency, so that's why radio waves, microwaves, they're not really, in terms of electromagnetic waves, right, they're not really, let's say, dangerous for us, but X-rays, gamma rays are dangerous because they have large frequency. All right, so this is in terms of the intensity. Intensity is power per unit area. That means, uh, how much energy per unit time per unit area going through that length L of the medium. Now, if a wave is able to spread out, let's say three-dimensionally, for example, if you have a sound speaker, right? When you have a sound speaker and you play music, you can hear the music from in front of it, to the side of it, back of it, up, right? So you can hear it from everywhere because the energy, right, from that source is spread out in every direction, the waves. That's more, let's say, generally what happens, right? So the sound source uh, kind of like moves in three dimension. Let's say if it's a water wave, you see sort of like as a two-dimensional moving in a plane. But let's say most of the time you can think of like, you can have a three-dimensional wave moving, spreading outward like that. Okay, so these are known as a spherical waves. So wave is spherical. So just from a geometrical consideration, as long as the power output is constant, we can see that intensity is proportional to 1 over r square. Okay. So intentionally proportional to 1 over r square, because intensity is power per square area, right? And area for a sphere is 4 pi r square. So that means if, the power output is constant, which means that, let's say P here, right, power output is constant, then intensity just, can be only changed due to the r square, 1 over r square. That means you go from this point r1, this point r2. If you're changing the distance, then that's how you change the intensity. And you can see, right, you double the distance, intensity decreases by 4 times, because you're assuming that this is constant. The only thing changes intensity is the distance, and it's an inverse square law relationship. All right, here's an example. You have a 100-watt light bulb, produces 5 watt of visible light. The other 95 watts are dissipated as heat and infrared radiation. Okay, that means, you get only 5 watt technically as effective, amount of energy that you use. So what is the light intensity on a wall 2 meters away from the light bulb? All right, so let's look at this example, this part first. So again, in terms of what we know here is we are trying to find the light intensity. And we know that intensity, this is for part A, right? So intensity in terms of power divided by surface area. Okay, so it's a light bulb, so the light, spreads out as a spherical wave, right? So, and we're given in terms of the 5 watt as sort of like out of that 100 watt as a effective, let's say power output. So we do 5 watts divided by 4 pi r square. So that's basically my distance, right? So let's say if here's a light. So let's say if this is a light bulb. So let's say there's a filament there. So it starts spreading out, right? So let's say here's then the wall. So then you're looking at, R, which is then 2 meter long. That means, in terms of what is the intensity when it hits the wall. So then 5 watts divided by 4 pi 2 meters square. Then we get 0.095 watt per square meters. That's the intensity of that light. Okay. So now what happens, let's say if I would consider 2 meters in the opposite direction, 2 meters in the opposite direction where there is no wall, would you have the same intensity? Well, yes, because you have just same equation, 2 meters in this direction, 2 meters in that direction, 2 meters in this direction, doesn't matter, right? So basically it's a spherical, let's say spherical wave, right? When it spreads out, its intensity is just position dependent, not, let's say, wall dependent or screen dependent or, I don't know, water dependent, right? So that means it's going to be pretty much the same intensity depending on where it is. Let's look at part B. It says a krypton laser produces a cylindrical red laser beam 2 millimeters in diameter with 5 watts of power. What is the light intensity on a wall 2 meters away from the laser? Okay. So one of the things we have here is this. So if I'm talking about, now here's the wall, here's my source. So let's say here's a laser like this. One thing about the laser here, when it generates a beam, I don't know what color is this one, right? But let's say it generates very specific, let's say a beam. It's not a wave that's kind of spreads out like that. Okay, so it's a beam that, only, let's say, what is it, 2 millimeters in diameter, right? So it doesn't really spread out. And beam here basically is in this 2 meter diameter, right? So which means that it's, if I'm looking at the intensity, which is power per, surface, then on the wall, it is basically generates a circular light. That means this is 5 watt divided by then, area in a circle, right? So this basically just an area of the circle is just pi r square. Okay. So then if I, again, plug in those values, right? 5 watts over pi times, you know, um, half of the diameter, 2 millimeter, right? 0.001 meter square, right? So if I calculate this, then I'm going to get 1.6 megawatt per square meters, like that. All right. So again, in terms of for this one, right? So we are looking at a very, in terms of, it doesn't spread out, so it only generates light at exactly that, a circle with a 2 millimeter diameter. So that's why, in terms of its intensity, is much higher, right? You can say that this is just basically what is it, one, two, three, so 95 thousand of it, right? So point, it's a milliwatt. The other one is a megawatt. So mega is million, milli is a thousand, right? So it's a factor of like 10 million or so difference between them, right?